So, we have talked a lot about direct search methods when you have an interval that you're searching over, but that's not always going to be the case. You might just be given a function and asked to find its minimum without knowing where to start. And so that's an unbounded search problem, and that's what we'll talk about here. Okay, so we've talked about these bounded problems, where the big feature of these, we assume we know nothing about the differentiability of f, which is nice, but we assume that our function maps from some closed interval, a, b, onto the real numbers. And actually, if you think about it in terms of practically doing optimization, particularly if you've just got a black box function, that's not particularly useful in a lot of ways. In general, if you're just handed some piece of code that takes in numbers and spits out other numbers, right? Maybe it's some complicated weather model or a disease model, or some computer graphics thing or something like this, or some algorithm for playing chess or whatever, then you don't necessarily know what the interval is over which that function is going to be unimodal, right? So you don't know where to start. So it's actually a pretty realistic thing that you're not going to know this interval a to b, and so you can't use this bounded. You don't have a bounded problem. What we really would like, in a lot of cases, is to solve this problem, where let's assume that we still have a unimodal function, so something that's got a unique minimum and it rises on either side of that minimum. But let's relax this idea about the closed interval, about the boundedness. It's just a function that maps from the reals to the reals. It takes in numbers and it spits out other numbers, and it assumes nothing about the differentiability of f. So it's just a black box function. So the key feature of that is that we're generalizing now to just functions that go from the reals to the reals. So you don't naturally have a bound on the numbers that you can feed into this thing. And so the question is, how do you actually use a search method to find the minimizer of this? So actually the big idea with this is to do something pretty simple. The big idea is to essentially take our unbounded problem, right, where we have no idea what AB is, and turn it into a bounded problem. So the idea here is that if this is a unimodal function, so long as we can find some interval that covers over, that goes over the minimizer, the minimum of that function, then we can use our bounded approaches. We can use our dichotomous or our golden section search or whatever we want. So if we can find an AB here that contains the minimum, then away we go. We can just use everything that we've learned so far. So how do we do that? How do we find an interval that covers the minimum? Well, we've seen since the start, if we can find 3 points at which the function value goes down and then up, right? So 3 points where the middle point is lower than the other 2, then we know that there has to be the minimum for a unimodal problem somewhere in that interval. Right? So the idea for this is essentially to pick a point, x0, evaluate the function there, evaluate a point near it, so another x1, and hope that that's heading downhill. If it's not heading downhill, then search in the other direction. And then keep evaluating a third point, keep going further and further and further out, and we do this geometrically, such that such that you find you cover over the minimizing point at some point. So the first thing that you do is evaluate some x2, so double the interval between x0 and x1 here. So this width would be 2h. Evaluate that. Evaluate the function value there. It's still going down. It's not going back up. So the minimizer can't be in the interval x0 to x2. So we double and get larger again. So now do 4h. And evaluate the function value at x3, right? And so at x0, x1, x3, or even x1, x2, x3, the function's still heading downwards, so the minimum's not in there. So we'll go to x4, here, evaluate that. So this would now be 8 times larger than our original interval. And then I've got a selection of 3 points, x2, x3, and x4, or any of these, x1, x3, x4, x0, x1, x4, or anything there that cover over the minimum of this function. I guess I can't do x0, x1, x4 actually because they're going down. So if I take x2, x3, and x4, then I've got this dip. And so now I know the minimizer is in that interval, and so I can do a bounded search problem using starting from the interval x2 to x4 as my A and B. And that's it. And this is quite efficient because we're going to do this increasing distance between each pair of these points, and it's increasing geometrically, so it's doubling each time. That's that's going to get very large very quickly, and so I'm going to be able to find the minimum, or find the interval that the minimum lies in. So here's some code for this, and all this does is, there's a step here that checks, if you start from an initial point x0, if you evaluate the point next to it, if you evaluate a point to the right of that, if it's larger, then flip around, try and head downhill all the time. So there's a check there to go left or right. If not, then just evaluate a third point, so x0, x1, and x2, where the distance between x1 and x2 is twice as large as what it was between x0 and x1, and then keep repeating that until such time as you get a point that is larger, higher again than the one next to it, and then you just decide what the interval is. So here's an example that we just did before. So finding the minimizer for this function. Right. So if we didn't know anything about the interval here, we didn't know to start at 1 to 9. Let's just see how quickly it would take us to figure out where to go there. Now we need to cheat kind of with this function, or just draw it up on the board. Right. So there's our function. It's got a minimum at around 2.5 or so. I'm going to say that let's just extend that so that make sure that this function is unimodal. If in the original function, if x is less than 0, then the function is not defined. So we'll just cheat. We'll add a branch on there that makes it unimodal so that we can do this. And let's say I don't know anything about this. I'm going to start. Let's say we'll choose some bad initial guess for this. We'll choose x0 equals 10, and then we'll try a step size of 1. So the first function value that we'd evaluate would be at x0 equals 11, right? And then that's going to be higher. Right, so I actually need to go backwards with this. So I do one extra piece of work to decide that to head downhill I need to go backwards. So I'll evaluate here x1 equals 9. Right, let's just take a step size of 1 just for the sake of it. And then I'll evaluate x2. That's double that width again away. So x2 is going to be at 7 as the next one. We're still heading downhill there. This is the minimum here turns out to be between 2 and 3. So x3 will double the interval again. So subtract 4 from that. And then x4 will subtract 8 from that. We'll get to -5. -5 now certainly covers the, if this is just, let's just say that's going up linearly here in my new function. And so this certainly, works. So I'd take my interval here to be -5 to 7. And then I could use my golden search and my dichotomous search. And that would be very quick. And so there I would have actually done 1, 2, 3, 4, 5, 5 iterations to get to that. And so that's how that works. Just to drive the point home at how quick this is, let's say that we were even stupider in guessing where the minimum of this function is. We had no idea. We did math wrong, we guessed wrong, and we said that, we figured that x naught might be somewhere around 100. So the first thing that we'll guess is x1 is 101, but my function's going to be increasing forever, so I'll head back in the other direction. So we'll take x1 be 99, and then I'll double the interval and subtract, go to x1 equals 97, double it again to a width of 4, and subtract, so that's 93, double again to 8 and subtract, that's going to be 85, x5, put the left-hand interval at 69, doubling again, still a way away, 37, we're still miles away, right? But if we do one more iteration, then I've gone a width here of 1 to 2, 4, 8, 16, 32, going up to 64 here is going to give me minus 27. And then minus 27 is way over there, so I definitely have something that's stepping down and then up. And so my starting interval AB, there would be still pretty large, negative 27 to 69. But how many iterations have I done? I've done 1, 2, 3, 4, 5, 6, 7, 8. Only 3 more than in this example, despite being miles and miles away. So to turn an unbounded problem into a bounded problem is really quick. You don't actually have to do all that much. You don't have to do all that much at work at all. So that's cool. So we can actually turn our bounded problems into unbounded problems with a pretty simple algorithm. We have to do a little bit extra computation, but not too much. So here's the strategy. If I'm faced with an unbounded problem, then I can use this geometric search idea. We sort of split this into 2 search problems. So the first problem is to find the bounded interval, the closed interval, which contains my local minimum. And a geometric search is a good way to do that because it gets very large very quickly. And once I have AB, I can use my machinery of bounded search methods, my dichotomous or my golden section search, to find the minimum on that interval. So I just split it into this 2-part problem. Okay, so that's going to be pretty much all we have to say about direct search. So just to summarise it really quickly, why should you care about these methods? These are sort of ancient methods in optimisation, actually. But they're a good thing to talk about because they're actually quite general. The first thing to say about them is that these direct search methods, they really assume nothing about the function, apart from that it's unimodal, right? So apart from, they don't, when I say nothing, I mean nothing about like differentiability. You don't have to be able to evaluate any other properties of this function. You can just have a piece of code that spits out numbers. And you don't need to know anything about how to differentiate it or anything like that. And that's going to be unique amongst the methods that we're going to talk about. And you can adapt these things. You can work on bounded or unbounded problems, which is cool. And some other things, we talked about for the dichotomous and the golden section search, we can calculate before we actually do anything how many iterations it's going to take to get the solution to within a given accuracy. And that's actually really useful, right? So even though I don't know anything about this function, if you tell me how accurately you want to know the solution, I can tell you how many iterations, how many times I'm going to have to loop through this thing. So, which means I don't necessarily need to break my computer, in something that's going to take it forever to converge. That's also pretty unique amongst the methods that we're going to look at. It also doesn't take any memory, right? You don't actually have to store anything much at all. Like when you look at the code for these things, for the golden section search, all I had to store was 4 function values, right, at these 4 points in the interval. And it's only 5 for the dichotomous search. So there's nothing to actually store. So this optimization is really trivial on computer memory, which is cool. And also simple methods like these are explainable. I think there is a power in things where you can explain the method that you've used to optimize your function really simply, without needing too much calculus or anything like this. From here on, we're going to get into stuff where we need some more mathematics, some more high-powered mathematics. We'll next talk about how we can be a little stricter on some of these assumptions up here, and how we can build optimization methods out of that. That's it. Oh, long one, 16 minutes for that. That was probably longer than it deserved, actually, that topic. Because I used the whiteboard. This is kind of the point where we have to start concentrating a little bit. We actually have to start thinking and doing a little bit of math from here on out.